Hello guys, welcome to Solving Solutions, your number one channel where you get solutions to all your solving problems. It's nice having you in class again today. How have you been? We are going to look at something very interesting in solving. We are going to look at adjustment computation, and then we are going to look at how you can use it to in, let's say, adjustment of a network, or adjustment of a network. So before I proceed, I would like to acknowledge the support of my senior colleagues and my former lecturer, Sobio Olani Saga, right? Yeah, Sobio Olani Saga, and hydrographer Odunaike Olalekon. They really guided and they supported in coming up with this content. So I want to say a very big thank you to those guys. Or yeah, they are my senior colleagues, to those guys. All right, now let's now look at the question we have on ground. We are given a particular question, and we are given the coordinates of two known points, and we're also given the provisional coordinates of one unknown point, which is C. This point C is unknown. These 2 points are known. We are given the bearings of AC, and we are given the bearings of BC. We are given their distances as well, and we're also given an angle that was observed at this point or so, right? Good. Now the question is that we should determine the coordinates of point C, which is this unknown point. We should determine the coordinates of point C using what variation of coordinate method. Now, variation of coordinate method is actually it's used in the network adjustment, and it helps to calculate the best estimate for all points in the network. The best estimate for all points. In surveying, maybe whatever measurements we carry out or we have, it is believed that there's a measure of error in it, and we cannot completely eliminate. We only detect, or let's say determine, the error and reduce it to the barest minimum. I believe that's some of the basics of adjustment computation as we were taught. So we want to know the most probable value, the most probable coordinate of this point C, having known the coordinates of point A and being given what the provisional coordinates of what point C. So it's going to be an interesting class. It's be quite long, and we would want you to have your calculators by you because we have our calculator here, or I have my calculator here. So please, you need to follow us through as we instruct you on what to press on your calculator, and you can see your results being displayed on the screen, right? Good. Now, as we said earlier, we are using what the variation of coordinate method of least square adjustment, and there is a note here. The method of adjustment is basically a least square method using an observation equation, and it's virtually the standard method for network adjustment. And there are different reasons, because it doesn't rely on the formulation of condition of adjustment, which may be difficult. This is actually a note from my lecturer, Savio SS Olani. Yeah, Said Saga Olani. All right, now let's look at how we can tackle this question. First thing is that let's look at the parameters. We are given an angle, which is ACB, right? We are given a length, which is AC. We are given another length, which is length BC. We are given a bearing. That's why we indicated the north here. So the arc distance from the north towards the other point is actually the bearing. So we are given the first bearing here, and we're also given the second bearing, right? Good. And according to the question, it says for two stations A and C, the coordinates are given. The following observations were made on station C. Now, this is very important. The following observations, that means all the observations you can see, I mean the bearings and the angles, were made on what? On station C. As we proceed, or as we progress, you would understand why the emphasis needs to be laid on where the observation is made. Else, you might get your equations wrong, right? Your observation equations, you might get them wrong. So, this particular question, the observation was made on station C. Observations were made on what station C. So if the provisional coordinate of C have been taken as this, determine the coordinate of C by method of what? Variation of coordinate. Are we together? Now, to get the distances and the bearings of the lines, we need to perform back computation. I hope you're following through, please. To get the distances and the bearings of the lines, line AB or line AC or line BC or whatever, we need to what? Perform the back computation. Then we can now form our L matrix. Our L matrix is actually the matrix of what observed minus computed, right? Where your O is observed and your C is what the computed values. Are we together? Your O is observed, your C is computed. As we progress, you know what observed means and you know what computed means. So now, from the equation, we have number of observations. We have 5 observations because we have what? We have the length, we have the bearing, the length and bearing of AC, we have the length and bearing of what BC, and then we also have the angle observed at what at station C. So you can see we have 1, 2, 3, 4, and 5, right? Good. And then the number of parameters are actually 2 because what we need is delta nothing and delta easting of station C. Are we together? Which we are going to apply to the what do you call it? To the provisional coordinate of C that was already given to us, right? Are we together? Good. So now this is the normal, or let's say this is the formula we are going to use. A transpose A multiplied by the weight A transpose multiplied by the weight multiplied by A, then you find the inverse multiplied by what? A transpose multiplied by the weight, and then what? The L matrix multiplied by the L matrix. You are going to see the elements of all of these matrices as we what? As we proceed. So we have AT, which is A transpose P A inverse, multiplied by what? AT, which is A transpose PL, right? Good. So now let's look at this particular what we call it. Let's call it the back computation of the points, right? Good. So now let's see how we would get the back computation of the point. You know, the coordinate of A was given to us, which you can see 11064.76. That's the northern. Then 4006.99. That's the eastern, right? Then we have that of B, we have that of C. And for us to have a closed loop, we are going to repeat that of what? A, right? Good. So these are actually some basic stuff. For us to get the distance and bearing, because that's what we want to get. Remember, that's what we told you we want to get, right? So for us to get the distance and the bearing between A and B, what we are going to do is that we are going to carry out the back computation. So it will be the coordinate of B, the eastern coordinate of B, which is 7582. Please press it on your calculator to confirm. You need to press these things on your calculator, please. So we have 7582.46 minus 4006.99. You're supposed to have something like 3575.47 or so, right? Good. Then if you do that of the nothings, you should have minus 2581.47. Please, are you pressing that? Are you pressing that on your calculator? You need to press it on your calculator so that you will be sure if we arrive at the same what? At the same value. Good. So when you have your delta nothing and your delta easting, you now use the command on your calculator. If you're using the Casio series, just say shift and then you press the plus sign. You should see pole coming up, right? When you see pole coming up, the next thing is what? You impute your delta nothing, which is minus 2581.47, then comma your easting, that's your delta easting. We have 3575 point what? Point point 3575.47 as well. So we have a distance of 4409.986. Are you pressing that on your calculator, please? Good. And then for you to have your bearing, you say alpha y degrees on your calculator. So you should be able to see something like 125 degrees, 49 minutes, 44.69 seconds. Please press that on your calculator. Ensure you arrive at the same value as we did, right? Good. So that's the distance and bearing between what? AC. So all the values you see under this our back computation columns are what? The computed values. They are what? The computed values. However, this bearing has already been given to us at some point, right? This bearing, okay, the bearing AC was not, sorry, AB was not given. We only have bearing AC and what? BC. All right, good. So this AB was not given. So you are going to see this BC now from your from the question given to us, or let's say from the question given to us. So let's come to get our what our bearing BC. The same procedure, the easting of C minus the easting of B, then the what? The northern of C minus what? The northern of B. So your delta easting should be 950.920. Was that what you got? Please, if you did not get the answer, you need to try it again. You will have to get the answer. Thank you so much. Then your what? The northern of C minus what? The northern of B you should be able to come up with what 3701.23. Are we together? So when you have your delta nothing and your delta hasting, you can now use that pole function on your calculator, which is what shift plus. When the pole command comes up, the first thing you are going to type is what your delta nothing, which is what 3701 point what 23, then comma your delta hasting, which is what 950 point what 92. So you should be able to see 3821.433 on your calculator as the distance, right? It is depicted as R depending on the version of the cartridge you're using. Then your bearing is depicted as theta, right? So when you want to convert that theta to degree meter and seconds, you just say what alpha y degrees and you say what equal to. Please, if we are too fast, you can just pause the video, you rewind, and you get what we are saying, right? Good. So we have what 14 degrees, 24 minutes, 31.66 seconds, right? So that's the bearing between B and C, and then this is the distance what between what B and C. So you do the same thing to get what distance and bearing between what A and what A and C. So having done that, you have been able to determine what the computed values. You have been able to what determine the computed values. Remember, we told you were going to need them on a particular matrix L, right? Which is what observed minus computed, right? Good. So now let's go back to that. Good. So as we told you earlier, you need what O minus C, which is what observed minus computed. And all the values you saw on this our back computation table are all the values for what? For computed. So we are now going to show you the next slide where you will now see how we came about what our observed and computed. Good. Sorry. Now we have what from the question bearing AC is what 76 degrees 6 minutes 29 seconds. This is what we mean by that. You look at the question, the bearing that was given to us, this plus minus 4 seconds is actually the standard deviation. You've seen them here. The standard deviation of the length is 0.05 meters plus or minus. The standard deviation of the angle is what 5.6 seconds, whereas the standard deviation of the bearing is what is 4 seconds. So these values will be needed in our weight matrix. It will be needed in our P matrix, right? It will be needed in our P matrix. We are going to see that as we progress, right? Good. So now you can see the bearing of AC given to us is what 76 degrees 6 minutes 29 seconds. Now let's go back. Now from the question, the bearing AC given to us is what 76 degrees 6 minutes 29 seconds. However, from the back computation, that's what BC means. From the back computation, we got 256 degrees 6 minutes 17.53 seconds rather minus 180. Now the reason why we added 180, let's go back there. Now look at the back computation. What we have here is CA, not what? Not AC. What we have here is what? Is CA, not AC. And you know that when you have AC and you have CA, their difference is always what 180 because they are what angle on a straight line. Let's just use this as an example. If you're moving from A to C and you moved 14 degrees, when you're coming from C to A, your bearing will be what 14 plus what 180, which should be something like 190 something, which is 194. So that's what we want to do here, right? So when we say from the question AC is 76 629, however from our back computation we got 256 6 minutes 17.53 seconds minus 180. The reason why we are subtracting 180 from it is that what we have is the back bearing, whereas what we need is what the forward bearing. Therefore, we need to subtract the forward bearing we need to subtract 180 from the forward bearing to get our back bearing, which is what our AC. So we denoted it as what the bearing AC is equal to the bearing CA, which is what we got from our back computation, plus or minus 180. Now, plus or minus depending on which one is bigger. If the value is like as this is bigger, we subtracted 180. If it was smaller, we have to add 180 because we need to get a positive value, right? Good. So we subtracted 180 from it, and we have what 76 degrees 6 minutes 17.53 seconds. So that is the computed. That is what the computed value of what bearing AC. I hope we are not too fast. If we are too fast, you can pause and you can rewind and ensure that you have your calculators with you. Thank you so much. So now let's come back to our observed minus computed, the elements of our L matrix. So the observed minus computed for the line AC, we are going to have what? The bearing. We are going to have the observed, which is 76 as given to us in the question. 76 degrees 6 minutes 29 seconds minus what we computed from our back computation, 76 degrees 6 minutes 17.53 seconds. Please confirm this value on your calculator. You should be able to arrive at what? 11.47 seconds. Are we together? Good. Now let's come to the next one. We have what? For line BC. Now for the line BC, the observed as given in the question is what? 14 degrees 24 minutes 27 seconds. However, what we got from our back computation, you can actually go back and confirm it. What we got from our back computation is what? 14 degrees 24 minutes 31.66 seconds, right? Good. By the time you do your observed minus computed, you should be able to come up with what? Minus 4.66 seconds, right? Good. So we are done with all of the bearings. Now let's come to the length, which are the distances. Again, for distance AC, which is this same distance, the observed, that's what was given to us in the question, is what? 4663.08 meters. However, when we did our back computation, what we got was what? 4662.839 meters, right? Therefore, our observed minus computed, which is part of the element of our L matrix, is what? 0.241 meters. Ensure you confirm this on your calculator. Please, you need to press it. Now, for the distance BC, which is this other distance, we have what? The observed given to us from the question to be what? 3821.21, right? 3821.21 meters. Whereas from our back computation, what we got was what? 3821.433. Therefore, the observed minus computed, as you can see here, is what? Minus 0.223. Are we together? Good. That is for the distance. Now we also need to get the angle. That is, remember from the question, as you can see, they gave us an angle ACB. And you know, mathematically, from maybe our basic mathematics, when you have notations like this, the middle point is actually the observed station, right? Then your first is your back station, and then your third is what? Your forward station. So this is just basic mathematics, and we are going to apply it now. Good. So that's why you can see this note here. We have ACB as noted, or maybe as denoted rather, in the question. So we know that C is our what? Our instrument station. A is our backside, and what? B is our foresight. And in adjustment completion, when you want to carry out the, like when you're drawing the conventional denotations or something, you have what? Your instrument station as this, as represented with I. You have your backside as represented with J, and then you have your fore station represented with what? Your back station, and then represented with J, then your fore station represented with K. So these are denotations that are used, let's say, in adjustment completion, or as we have used in our video here, right? Good. As we have used in our video here. Good. So now we have what? Backside, intermediate side, sorry, instrument station rather, not intermediate side. We have backside, instrument station, and what? The forward station. We have what? ACB. Now, the essence of making this emphasis is that it is very, very important you know these denotations, because as we progress, you are going to see, okay, as you can see on this other side of the note, you can see different equations. These equations are very, very important when you know what is your instrument station and when you know what is your backside. Are we together? Good. So now, having established that, to get the angle ACB, let's have a sketch. Now, let us look at our sketch. From the back computation we did, our bearing AC was 76, and 76 is actually in the first quadrant. So we have what? A to C to be somewhere around there. So you can see the quadrant, right? It's actually still on the first quadrant, right? Good. That's bearing A to C. Then the next one is, we also have for bearing what? C to B. However, we don't have C to B directly. What we have is BC. Let's go back there. What we have is what? BC, and our BC is what? 14. So since this is 14, what we need now is what? C to B. So what we are going to do is what? 14 plus 180, which is around 194. And you know 194 is just after the second quadrant of 180, right? So you can see it's just below 180. Then you go to this point. Then the next thing is what? B to A. What do we have as our B to A? What we have as our B to A is what? This is 125. So 125 plus 180, you should be able to come up with, sorry, we have 125 plus 180. Please ensure you press in your calculator. You have 305, right? Then if you look at it critically, 305 is after your third quadrant, is actually in your fourth quadrant. So you can now see how it goes. So if you don't want to go the way we went, you can go from A to B, from B to C, from C to A. Whatever, okay, no matter the direction you follow, in as much as your bearings are correct, you are good to go. So this is actually our sketch. And from this sketch, what we need is this angle at this point, because angles are measured at a point. What we need is what this angle at this point, which is this. That's what you can see. So for us to have this angle at this point, that's why we say this implies that our angle ACB is equal to the back bearing of AC, which is this. This is the forward bearing, right? So to be the back bearing of AC minus what? This other one, BC, the back bearing of BC. Because the reason why we added 180, the reason why we called it what back bearing is because we added 180, right? So now if you have what AC, remember what our AC is. Our AC as we got here is what 76, as you can see, right? Good. Therefore, the back bearing, which is plus 180, will give you what 256, 6 minutes, 17.53 seconds. Please, if we are too fast, you pause the video, you rewind, and you will get it. And ensure you have your calculators, because these things are very important. When you press them on your calculator, you're actually following us through, right? Good. Now, the next one is what your BC. Now, the BC, as we got from this our from the other side of this our material, we have something like where is our BC, please? Good. We have 14 degrees 24 minutes and 27 seconds, right? That's the BC. So by the time we add 180 to it, as we have indicated here, we have what 194 degrees 24 minutes 31.60 seconds. So when you find the difference between these two numbers, you are going to have something like 61 degrees 41 minutes 45.87. So this will now be our computed angle. This will now be what our computed angle, which we are now going to use with the observed as given to us in the question. The observed as given to us is what 61 41 57, right? Good. Which is given to us in the question as 61. Where is it? 61 41 57. So by the time you find their difference, you should be able to come up with what 11.13 seconds. Please, you should be doing this thing with us. It is very, very important, right? Good. Now, from the question, we have two bearings, two distances, and one angle. Therefore, let us write out the respective equations. Now, we have told you from the beginning, this is what we mean by that. We've told you from the beginning the number of observations, the number of parameters, right? Good. That's what we try to just note here. We have two bearings, two distances, and one angle, 2, 2, 1, which is 5. Therefore, let's write out their respective equations. Now, their respective equations cannot just be written out. We have a generic equation, or we have generic equations rather. We have generic equations for angles, for distances, and for forward bearings, as used in what variation of coordinate method of least square adjustment. So these are the denotations here. For the angle, remember that as we have stated here, you have an instrument station, you have a back side, and you have a forward side. A forward side, right? Good. That's why you have what the angle JIK. So what this simply means, let's just explain it through. What it simply means is that there were deductions, or let's say there were proofs. We are not going to go into those proofs. We are just going to extract the proof. Yeah, we are just going to extract the final values, and we are going to use it, which is the equation as you can see. So this is the delta E1. This is what delta EI rather. Now this I and this I represents what your instrument station. This J and this J represents what your backside. And then we have K and K here, which represents what your foresight. This is just the simplest way you will understand it. By the time you get to the literature, maybe any textbook of adjustment computation, maybe any material given to you, and you find it difficult, just remember what we just told you. Your I is your instrument station. Your J, as you've seen here, is what your back station. Then your K is what your forward station. So with this, you should be able to know how to apply it. Then these are their respective coefficients. For the delta easting of your I, you have what K1 minus K2. You are going to see the legend somewhere down here. You have K1 minus K2. Then for your delta nothing of your I as well, which is your instrument station, you have what L2 minus L1. Then you come to your J. The coefficient of what your delta easting for J, which is what your backside, is what minus K1. Then the coefficient of your delta nothing for that same backside is what L1. Then you come to your K. K is what your foresight, right? Good. These denotations are for angles. They are for angles. So when you come to your K, the delta easting for your K, which is what your foresight, the coefficient is what K2. Then the coefficient for your delta nothing is what minus L2. So by the time you are able to understand it like this, as we progress, you are going to see the beauty of it. Good. Now they are all equal to the observed minus computed in seconds. You are going to see what we mean by in seconds, because we are going to convert our distances, or let's say we are going to convert our distances to their equivalent in bearings, right? Good. There was a note I wrote. Let me confirm. To convert the linear parameters to angles. Good. We are going to convert the linear parameters to angles, and we are going to multiply it by a constant, which you are going to see very, very soon. So having established that for the angle equation, let's come down to our distance equation. Unfortunately, we did not draw any diagram for our distance equation, but we can still use this. Now, distances are between 2 points, right? Let's say A and B, or B and C, or C and D, or whatever, right? So let's say we are using A and B, which are these 2 points. So your A represents your I will represent your A, and then your what your K, sorry, your J will now represent what your B. So your I is your instrument station, and then your J is what your forward station, because you don't need a back station for angles. You only need 2 points where you are setting up and where you are measuring your distance to, right? So we are using A and B. So for your distance, Lij is equal to what? The coefficient of delta easting for your instrument station, which is I, is what? Minus P. Then the coefficient of delta nothing, which is where you the alternate of your instrument station, is what? Minus Q, right? Plus, then you now move to your forward station, which is what? J, as we have told you earlier. Then the coefficient of delta easting for the forward station is what? P, plus P. Then that of delta nothing is what? Plus Q, all equal to observed minus computed in what? In seconds. So that's the general. All these are general. We have not started extracting it to suit our question. These are general. Then finally, for the forward bearing, because we have that of the back bearing as well. For the forward bearing, we have IK. Remember that for bearing as well, we just need 2 points. It's only on the angle that you need 3 points, right? Good. Angles at a point, you observe the angles at a point, but you need 2 other points to reference to. But for your bearing, with reference to your true north, you just move to any direction. So you need just 2 points. That's why you can see IK only for what? For your bearing, and you can see also Ij for your distance. But for your angle, you were seeing JIK, because you need 3 points to get an angle, but you need just 2 points to get a bearing. Please pay attention or take note of these important concepts. Good. Having said that, let's now move on. The next thing is that we also need to explain this forward bearing equation. So we have the bearing IK. Now the IK is actually forward. Remember we told you these denotations earlier, that when you say K, you are referring to what? Your forward station, right? So that's why you see IK. So now the coefficient of your delta easting for your instrument station is minus K2. The coefficient of delta nothing for your instrument station is what? L2. That of delta easting for your forward station, which is the K, is what? Plus K2. Sorry, the first one is minus K2. Then the second one is what? Plus K2. Then that of the delta nothing for your forward station is what? Minus L2. So as you can see this equation, you just need to take note of them. They are very, very important. Equal to what you observed minus computed, right? Good. Now the next thing is we now give the explanation of, let's say, like a legend, where your K1 is equal to cos theta, let's say cos bearing of Ij all over the length of what? Ij. By Ij, what do we mean? Let's say you have something like, you are going to see that in the example. Let's move on. So for cos K1, you have what? Cos theta Ij all over Lij. And the Ij here is what? Let's say we say J is your backside, right? Good. All over Lij. Then for your K2, you have what? Cos theta Ik all over what? Lik, which is what you have for your forward station, right? Good. Which is what you can see. What you can see here, right? All over Lik. Then for your L1, you have what? Sin theta Ij all over what? Lij, which is for your backside. Then your L2 is what? Sin theta Ik all over Lik, which is what? For your foresight. In fact, there is a note here where K1, K2, K1 is for your backside, then K2 is for your foresight. That's why we say K1 back bearing, K2 forward bearing. Good. Then your P the P we got from our distance equation are simply what? Sine theta ij for your P, then Q is what? Cos theta ij, right? That's for L1. Then you come down to L2, you have what? Sine theta ik all over what? Cos theta, sorry, sine theta ik, that's for P, and then your Q is what? Cos theta ik, that's for L2. Are we together? Good. So having established all of these concepts, or maybe yeah, should we call it concept? Having explained, let's use that. Having explained the parameters of this equation, I think it's high time we now look at how we can apply this to what our equation. So now the next slide we are going to show to you in this document is how you are going to now form your A matrix. By forming your A matrix, you are going to use these K, L, and P and Q, because these are the elements of what your A matrix. So let's show you the A matrix now. Good. Now to get the A matrix, we are going to form, let's say we are going to draw a table like this. Let's just say that we are going to draw a table like this. We have the delta nothing, sorry, the delta easting of C and the delta nothing of C, then the observed minus computed. Let's just leave this for now. So we have the delta easting of C and the delta nothing of C, because by the time we move it to Excel, we are still going to Excel. By the time we move it to Excel, you are going to see how we are going to go about it. So for your angle, sorry, this is your bearing 1, right? For your bearing 1, remember from the beginning, we have told you that the observations were made on station C. The observations were made on station C. This is very, very important for you to note. It's very, very important for you to note. Very, very important. Are we together? It is very, very important for you to note, because it's a key concept, it's a game changer in this question. So since the observations were made on station C, which means station C is what? Your instrument station, according to our denotation here, right? So if you're moving from C to A, your C will be I, and then your A will be what? Your A will be K. Are we together? Going by this our forward bearing equation, right? Good. Going by this our forward bearing equation, because we have I and K. So if your C is your instrument station, which is I, then your A, because according to the question given to us, we have AC, right? And we have BC. And we have been told that the observations were made on C, which means it went from C to A and then from C to what? To C to B. Good. So having established that, it means that what C represents our instrument station at both points, or let's say at each point, then the A and B represent our forward station at their respective points, so they are K respectively, and then C is constantly what? I. Please pay attention to this. Now let's move on to our A matrix. Good. Now on the A matrix, we have the delta easting of C, as we've told you, the delta nothing of C, and these are different coefficients. Now, how do you fill in these coefficients? Please, you need to pay attention. You need to pay very good attention at this point, because it's very, very important. This is actually a key point. Yeah, it's actually a key point on this video. If you miss any other thing, you don't need to miss this, and you are not supposed to miss any other thing as well on the video, so you don't need to miss anything. So now, how do you come about this coefficient, this minus K2? How do we know it's minus K2 and not something else? How do we know that it is L2 and not something else? So now let's go back to our equations. Good. Now on these our equations, you can see the notations for I, and you can see the notations for what? For K, right? And we have told you earlier that since observations were made on C, which means it is from C towards A, and then from C to B, which means C is your I. And you know that C is actually a point whose coordinate we want to adjust. This is actually a point whose coordinate we want to adjust. So you can actually apply this for traversing. Maybe you're moving from your control to point 1 to point 2, point 1, point 2, point 3 are not actually known. Then from point 3 you now move to another control, right? Good. When you move to that control, by the time you just understand the concept, you know how to maybe apply these equations. Yeah, how to apply these equations as you progress. So now let's come back. We have C to A, which means C is our instrument station, and then our A, or let's say A is what? Our our back side, right? Good. A is our foresight. I'm sorry. A is our foresight. So which is what? K. So since we are moving from C to A, which means C has error. You can see which is I, and then K, which is our forward station, does not have an error because it's actually adjusted. When we mean it has an error, it means it is not adjusted. We want to determine the, according to the question, we want to determine the coordinate of this point. So since we want to determine the coordinates, and what was given to us is the provisional coordinate, which means there are inherent error. It has a measure of error we want to detect and eliminate, right? Good. That's just the basic. So having established that C is having error, which means we are going to determine, we are going to find the coefficient of I. However, for A, which is our K now, we are not going to do anything here. So that's why we are now going to go back to, or we'll go back rather, that's why we'll go back to our A matrix, and you will see that for the first bearing, which is what AC, you find out that since it was observed on C, it's actually CA. Since it was observed on C, we have what? C, which is our I, minus K2. Are we together? Minus K2. Then our forward station, which is K, does not have any error. Are we together? Is this thing very simple? Is this thing very, very simple? I hope you're getting it. Now, let's go back there again. You can even see that on our table here for the A matrix, we only have for C delta nothing, delta easting of C, and then delta nothing of C. There is no other for A and there is none for B, which means whatever we are interested in is what? C. So whatever station C is, that is the coefficient whose we are going to take, or that's the coefficient we are going to take. Let's just use that. So wherever position C is, that's the coefficient we are going to take. Are we together? Good. So now we are still on the forward bearing equation. So since we know that C is our instrument station and it is I, so the delta easting equivalent, or the coefficient rather, of delta easting is what? Minus K2. That's why you see minus K2 under delta easting. And then the delta nothing coefficient um, for the instrument station is what? L2. That's why you see what? L2 under delta nothing. Same thing for CB. Since we are still using C as our instrument station, by the time you go down, we are going to show you on the next slide. By the time you go down, you still see what? Minus K2, because that's still our instrument station, right? I. Then for L2, we have what? For the delta nothing rather, we have what? L2. Are we together? So that's how we filled in that table. Now, before we move to that next slide, let's also look at that of the distance. Now, if you look at distance, we have what? AC. Is that not? But remember, we are observing from C, which means our C is our instrument station, and then our A is what? Our forward station. So now let's come to our distance equation, which is what? IG. Are we together? So since our I is our instrument station and that is C, which means that is where our error is, because C is where our error is. So what's the coefficient of delta easting for the instrument station I? Is minus P. Same thing for the coefficient of delta nothing for the instrument station is minus Q. That's why you see minus P and minus Q respectively under delta easting and what? Delta nothing. Are we together? So the same thing applies to the next distance. We have two distances BC. So still C as our instrument station, or where the instrument is observing to what? Observing to B. So we still have what? Minus P and what? Minus Q. These things are very simple. Please, if you miss it, you just pause and you rewind. These things are very, very simple. And we have tried to break it down to as simply as you can understand it. Good. Now let's go back to the table. Good. So you can see on the table, as we have explained, minus K2 L2 minus K2 L2, then minus P minus Q minus P and what? Minus Q. So we are now going to explain how you would go about getting what? Your K1 minus K2 and what? Your L2 minus L1 from the angle equation. Remember, this is angle. The first four we've done are for the bearings and for the length, right? Now we want to do that of what? The angle. Good. Now on the angle equation, as we have denoted here, we have what? ACB, which means C is our instrument station, A is our backside, and then B is what? Our foresight. Are we together? So having this on in your mind, you can be able to deduce how you can come up with the coefficients of each of those elements you need, right? Good. Now let's come. We have what I, we have J, and then we have what K and K, right? For delta easting and delta northing respectively, or let's say in each occasion. Now let's look at our A, C, and B. Well, look at A, C, and B. You know that A and B are already corrected, which represents in this our denotations J and K, which means we are not going to look at anything that has to do with J and K, which means we are not concerned with this second line. Are we together? Depending on how you are going to write it in your book, you are not concerned with anything that has to do with J and K. All you are concerned is with I. And why are you concerned with I? You are concerned with I because your I is denoting your instrument station, and that instrument station is actually the point of the coordinates that you want to determine, right? It's actually the coordinate here. That's the coordinate you want to determine, or that's the coordinate you want to adjust, as the case may be, right? Good. So since you know that I is actually the point C, which as we have actually explained to you here, since you know that I is the point C, the next thing you are going to do now is that under I, you now select the coefficients. The different coefficients, as you can see here for I, is what? K1, K2, which is K1 minus K2, that's for your delta easting. Then what? L2 minus L1, that's for your what? That's for your delta northing. I just hope this thing is very, very clear. Let's go over it again. We have what? IJK, and I is our instrument station, which is C. Then J is our backside, K is our what? Our foresight. So we don't need A and B, we need just C. And since C is I denotes C, or C represents I, or whatever the case we want to, maybe how we want to explain it, it means coming to our angle equation, we are just going to consider what? Our I. So considering delta easting for our I, we have the coefficient as what? K1 minus K2, and then we have for our delta northing, we have what? L2 minus L1. Are we together? That's why you can see these under what? Under that table. Now let's go back to that table. Good. As you can see on the table, you have what? K1 minus K2, and then you have what? L2 minus what? L1. Are we together? So you can see that they are very, very simple. Understanding the equations and getting your, let's say, yeah, extracting your coefficients from the question. Now from the equation rather. Now let's move a step higher, and we are getting to the end. Oh, we still have to go to Excel for the matrices. Good. Now let's see how we are going to do this. We still need to go to Excel. Very, very important, because these are actually giant matrices and you cannot do that manually. So for our bearing 1, we have minus K2. And from the legend we gave to you earlier, the formula for K2 is actually what? Cos theta. It was denoted by I, J, and K. But this time around, since we know what our I and J is, we are going to use the corresponding alphabet, the corresponding letter of the alphabet rather. So we have cos theta AC all over what? Length AC. And that cos theta AC means the cos bearing of AC, and the bearing of AC as we got from our back computation is what? 76 degrees 6 minutes 17.53 seconds. Please press this thing on your calculator. Remember, we told you that we are going to show you how to convert the linear parameters to angles, right? We told you something like that. So to convert those linear parameters to angles, you multiply the linear parameters by sine 1 second. Now, how do you get sine 1 seconds? Please press on your calculator. You say what? Sine 0 degrees 0 minutes 1 second. That's actually sine 1 second, right? Sine 0 degrees 0 minute 1 second. That's what sine 1 second. And you say equal to. So you should be able to see an exponential 4.8 4813 times 10 to the power minus 6. The values are quite long. So you ensure you save this thing on your calculator. So you save it as what? Shift store A. These things are actually on the video how to save, but perhaps we are going to make a special video for it. So you save it on your calculator so that you can always recall them. So we have saved it on our calculator as alpha A. We have saved it on letter A. So anytime we are calculating, or anytime we are moving on in these our calculations here, whenever we say alpha A multiplied by any distance, we know that we are multiplying that distance by what? Sine 1 second. Sine 1 second rather, because we have actually stored sine 1 second on what? On the letter A. Are we together? So these things are things that will make your work very easier and reduce stress. So now we have known what our bearing AC is. So by the time you press this on your calculator, you should be able to have something like 10.623. Please ensure you do that. But remember that there's a negative answer here. There's a negative sign here to the coefficient as we extracted from the equation. Therefore, we are going to still use the negative on our answer. We are going to use the minus on our answer, right? Which means the answer you're going to have here is positive by the time you do that on your calculator. But the reason why it is negative at this point is because of this negative sign here. So maybe if the answer you got was negative and you also have a negative sign here, so the two negative signs will cancel out to give you positive. But since the answer you got here is positive and you have a negative sign that is attached to the coefficient, which means your answer will automatically become what? Negative. So that's why you see negative 10.636230.5 and the rest of that. Now coming to L2. L2 is actually what? Sine bearing AC all over length AC. So we already know the bearing AC to be 76 degrees 6 minutes 17.53. So you just do that divided by the LAC. But remember, you need to multiply it by what? Sine 1 second. Ensure you don't forget this. That's why we said you should save it as A. So anytime you want to carry out the operations in your denominator, you just say alpha A times whatever distance, right? Good. So the same thing, you should be able to come up with 42.941409. Ensure you get this answer. Ensure you get this answer. Now let's move to the second bearing. Same thing we are going to do. K2 is actually what? Cos bearing BC divided by length BC. Remember that as it was given to us from the question, we have two bearings and two lengths, right? And then the first bearing is for AC, the second bearing is for BC. That's why you can see BC, right? All over length BC. So we know the bearing of BC to be what? Or computed as 14 degrees 24 minutes 31.66 seconds divided by the length, but we are going to multiply the length by 1 second. So you are going to have something like 52.277965 as the case may be. However, since there is a negative sign attached to the coefficient, your answer becomes what? Negative. Same thing, you come down to your L2. Your L2 is positive, so you don't have any issue. All you need to do is to do what? Find the sign of this your bearing of 14 minutes 24 14 degrees 24 minutes 31.60 seconds divided by the corresponding distance multiplied by sine 1 second. So you should be able to have what? 13.43125 as the case may be. So this is the value of what? Your L2. Now these values will be imputed into our A matrix on Excel. So pay attention to these values. By the time you're doing them, ensure you don't make a mistake so that when you want to type them on Excel, you can also type them as they are. Good. Now let's move to our lengths. We are done with our bearings. Let's move to our length. So the first length, for delta easting, we have minus P. And from the legend we told you earlier, P is actually what? Sine theta AC, right? And remember that there's a negative sign attached to P. So whatever answer you are going to have will be negative, right? So what's our AC? Our AC, we know it to be 76 degrees 6 minutes 17.53 seconds. There is no denominator here, so you just find the sign of that straight and then you attach the negative. Why are you attaching the negative? The coefficient of P here has a negative sign. Is that not good? Same thing for Q. For Q you have what? Cos theta AC. And what's AC? AC is what? The bearing of AC is what? 76 degrees 6 minutes 17.53. So by the time you find the cos of that particular value, you would have a positive answer. But the reason why our answer here is negative is because the coefficient is what? Is negative. I hope it's understood. Good. Now let's come to our second length. The same coefficients we have as what? P and Q. Now sine theta BC, because that's the second length, and our BC is what? 142431.66, as you can see it here. So by the time you find the sign of that value, you should have a positive answer, but it is negative in our answer because what? The coefficient is negative. Same thing for your Q. Cos what? 142431.66, 14 degrees 24 minutes 31.66. You should be able to have 0.9685449778, but it is negative. Are we together? So we are done with the two bearings and the two lengths. Now let's come back to our angle, which is what? K1 minus K2. So the first thing is what? We need to find K1. And from K1, we know that K1 is what? Cos theta CA. Now this time around, it's not AC. Are we together? It's not AC. So we have what? Cos theta CA all over what? L1. Are we together? Cos theta CA all over L1. And your CA is actually 180 plus your AC, and that CA will now be what, 256. We have good. We have AC here, so 256. 180 plus this 76 should be able to give you what, 256 divided by your L1. So since we have a length here, we are going to multiply that length by sine 1 second. So you are going to have something like minus. Now the answer you're going to have here is negative, right? Ensure you press this thing on your calculator. It's very, very important. The answer you're going to have here is negative. That's why our final answer is negative. Our coefficient is not negative, so negative and positive is what? Negative. So there is nothing that is changing here. Coming down to K2, we have what? Cos bearing CB, not BC, all over what? L2. So we have what? Cos 194. Our BC was 14. So 14 plus 180 should be able to give you what? 194 degrees 24 31.66 divided by the what? The length times sine 1 second. So by the time you do this on your calculator, your answer is negative, right? Good. So this negative does not have any, the coefficient here is not negative, therefore the negative holds. So ensure you do these things on your calculator. So now we have what? K2 minus K1. So our K2 is negative 52.277965 whatever. Then our K1 is what? Negative 10.62305043. So by the time you do this, maybe you find the difference in your calculator, you should be able to arrive at what? 41.6549149. Please do this thing on your calculator. Please do this thing on your calculator. This thing is very, very important. This thing is very, very important. Are we together? So you should arrive at what? This answer. Alright, there is a little typo here. This is supposed to be K1 minus K2, not K2 minus K1. As we were proceeding, we saw that the values are conflicting. The reason is because we were trying to confirm the answers in as much as we have written it here. So please ensure you do that with us. Now from our table, we have K1 minus K2, but there's an error here, it's a graphical error here, where we say K2 minus K1. However, the values are correct. So instead of K2 minus K1, please ensure you correct this to K1 minus K2. We are sorry for this mistake. K1 minus K2, which is minus 10.62. Yeah, K1 minus K2, not K2 minus K1. Please pardon us. So you have what? Minus 10.62305004 minus into minus this answer. So you eventually find out that this will turn positive, subtracting this. So you now have something like this. Are we together? So ensure you do that on your calculator. We take full responsibility of this particular typographic error. Now let's move on to our L2 minus L1, which is the coefficient of delta nothing of C. So upon coming to this point, we have what? Sine bearing CA, which is what's our CA? We already know what our AC is, which is what? 76. Therefore, CA will be what? 76 plus 180. So we have 256 divided by sine 1 second times 462.839. And we told you that sine 1 second simply means converting what? Your linear parameters to what? To angles, right? Good. So by the time you do this on your calculator, you should be able to arrive at this negative answer. So since the coefficient here does not warrant us to, they are together, so we are treating them together. So there's no need for us to change it or maybe multiply this negative answer by anything. So coming down to our L2, the same thing, sine bearing CB. We know what BC is. BC is 14. So CB will be what? 180 plus 14. So we have 194, 24, 31.66 degree meter seconds respectively, divided by sine 1 second multiplied by what? This is our length. So we are converting this length to what? To angular equivalent. So you should be able to arrive at what? This negative answer. I guess we made that mistake because we are trying to make the both of them the same, whereas they are not the same. This is K1 minus K2, whereas this is L2 minus L1. Please, we take responsibility for that typo error. So now coming down to this particular value, or coming down to this part of the material, we have something like what? L2, which is this last answer we have here, minus 13.4312573 minus into minus, because there are two minus now. So this will eventually turn positive. So it now be this value minus this. So you now have a positive answer of what? 29.5 101519. So this is actually these values. This is your K2, your L2, your K2, your L2, your minus P, your Q, your P, your Q, then your K1 minus K2, and then your L2 minus your L1 are all the elements of what your A matrix. And we are going to show you on Excel how you would multiply or how you are going to manipulate it. So we are going to see you on Excel very, very soon. Good. We are now on Excel, right? Now you need to pay very good attention. There's a video on the channel where we've shown you a bit of how to use Excel in Adjustment Computations, just about the matrices, right? Good. So now the first thing we are going to look at is we have actually imputed the values, or let's say, the values of the elements. We have imputed the values of the elements of our A matrix, and as we computed, our minus K2 is this, then our L2 is this, our minus K2 for the second bearing is this, our L2 for the second bearing is this, this is our minus P for the first length, this is our minus Q for the first length, then this is our minus P for the second length, our minus Q for the second length, then this is what the K1 minus K2 for our angle, and then this is what the L2 minus what the L1 of our angle, right? Then the L matrix, we told you that's the observed minus computed, and from the beginning, after we did the back computation, we try to do our subtractions, right? The observed minus computed, right? That's the O minus C matrix, if I'm not making a mistake. So from O minus C matrix, we are able to get 11.47 seconds for the first bearing. Then we're also able to get minus 4.66 for the second bearing. We got 0.241 for the first length. Then we have minus 0.223 for the second length. Then our angle was 11.13 seconds. Are we together? Good. Now let us look at this, our P matrix. Now the P matrix is a diagonal matrix, which actually uses the denotation of what the standard deviation. The standard deviation, as we have told you on the first slide. Now the standard deviation for our angle was what? The standard deviation for our angle was, let's confirm that, was 4 seconds, right? Good. That is standard deviation for our angle. It was 4 seconds. Now, according to the denotation, your P matrix is actually 1 over your standard deviation squared. Please take note. 1 over what? Your standard deviation squared. 1 over your standard deviation squared. 1 over, and that's why you can see it here, equal to, we actually built the formula, equal to 1 over the standard deviation. The standard deviation is what? 4 seconds squared. So we have something like this. So for the two bearings, they are actually the same. Then we now come down to the first length. The standard deviation of the length given to us is what? 0.05 meters, right? 0.05 meters. So 1 over 0.05 meters squared give us 400, right? That's why you can see 400 here, and you can also see 400 here. Now it's actually a diagonal matrix, whereby the elements at the diagonal are actually what? This 1 over the standard deviation squared for each of the observed entities, So for the first bearing, we can see the element here. For the second bearing, we can see that because the diagonal matrix, we don't need to come down, we don't need to go right, we just need to go along the diagonal, which is what we have done. And this is a 5 by 5 matrix. We have 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5. So we are going along what? The diagonal. So coming down to our length, which the standard deviation given to us was what? 0.5. So we have 400 for the first length. We have 400 for the second length, still along the what? The diagonal. Then coming to our angle. The angle that was given, the standard deviation for the angle given was what? 5.6 seconds. I'm sorry, 5.6 seconds. So we have 5.6 seconds squared 1 over 5 on the second square. So we have something like this. So all of these values you can see here, we are given to us on Excel, or maybe we are given to us from Excel. So we actually confirmed it with our calculator. So these are the elements of our P matrix. And our P matrix, as we have told you earlier, is what? The weight matrix, and we are going to use it in the formula. Remember the formula we quoted, A transpose PA in a bracket, then you find the inverse, is that not? Then multiplied by what? A transpose what? PL. You can see it here, A transpose PA multiplied by what? The inverse rather, multiplied by what? A transpose what? PL. Then this is actually the D we are looking for. This is actually the final answer. But this is the negative of D. Let me add negative here so that you know that this is the negative of D. So all the answers you can see here is what? Negative of that. The formula wants to mess up. Let's just keep it this way. So this is negative of what? D, right? Good. Now let's move on. So having imputed all of these elements, of these matrices, now we are going to proceed. The first thing we are going to do now is that according to the formula, we need what? A transpose. We need what? A transpose. And for you to have A transpose, you use the command what? Transpose. Now this is what? Row by column. That's how matrices are denoted, right? So we have row 1, row 2, row 3, row 4, row 5, and then column 1 and column 2. So this is what? A 5 by 2 matrix. Are we together? These are just the basic things in matrices. This is what? A 5 by 2 matrix. So when you transpose a 5 by 2 matrix, you are going to have what? A 2 by 5 matrix. You are going to have what? A 2 by 5 matrix. We don't need this. You are going to have a 2 by 5 matrix. So for you to use the transpose, you just define a 2 by 5 array. By a 2 by 5 array, are we correct here? 1, 2, 3, 4, 5. Okay, this is 6. So let's say we have 1, 2, 3, 4, 5. Good. This is a 2 by 5 array, right? Then on one of the empty cells, you say equal to, and then you type transpose. You do what? You type transpose. You double click on it. Now there is an open bracket asking you to define the array you want to transpose. So this is the array we want to transpose. So you highlight them. Upon highlighting it, you now say Control Shift Enter at the same time on your keyboard. What do you hold? You press Control Shift Enter on your what? On your keyboard. So you now find the what? You now find the transpose as it is being displayed here on this array. Are we together? You now see the transpose as it is being displayed on this array. Are we together? You can now see that what you have here is same thing as what you have here. Please, are these things very simple? Yes, they are very simple. Are you following? You need to answer if you're following. Please, if you have missed it, or maybe if there's any point you don't understand, you need to pause and you rewind. Are we together? Good. We are almost done. So we have what? Our A transpose. So that's how you transpose a matrix. Then the next thing in the formula is what? A transpose P. And these are P, which means we are going to multiply this matrix by this matrix. And in matrix multiplication, you need to know the row and the column. So we already know that this is a 5 by 5 matrix, right? And then this is what? This is the row by the column. This is what? 2 by 5 matrix. So the product we are going to have is what? A 5 by 2, or sorry, a 2 by 5 matrix as well. Are we together? So since we are going to have a 2 by 5 matrix, we also define a 2 by 5 array. And then we say equal to M multi. Now this M multi returns, as you can see on the screen, returns the matrix product of two arrays. An array of the same number of rows in array 1 and columns in array 2. Are we together? Good. So that's what we want to do. So what are we using first? Remember, in matrix, A by B is not the same thing as B by A. Are we together? If you say matrix A by matrix B, it's different from matrix B by matrix A. So you need to know the order. So according to the formula, we have A transpose P, not P multiplied by A transpose. Are we together? So we have A transpose P. So we are using this. So you select the whole of this. Sorry. Let's come back again. Let's define the array. Equal to M multi. Good. Then we are using the whole of this. So you select comma. Are we together? Then you now come to the next array, which is the next matrix, which is P. So you now select all of P. Then you still do what? Control Shift Enter. Are we together? So this is the second aspect. This is the second aspect, which is what? A transpose P. Which is what? A transpose P. Now the next thing is what? A transpose PA. Which is almost the first part of the formula. this is what A transpose P, as you can see. What we now need to do is what A transpose PA. So now this is what 2 by 5 matrix, and then our A is what 5 by 2. Therefore, by the time the both of them multiply, we are going to have something like a 2 by 2 matrix. So we just define a 2 by 2 array, which is this, equal to M mod again. Then we select the M mod. So what are we starting with? We are starting with A transpose P. So we select A transpose P, comma, then we now come and select what A, which is this, right? Then Control Shift Enter. You can now see that this value is actually the same thing as this value we got earlier, right? Good. So now the next thing to complete this part of the formula is to find the inverse. Of this 2 by 2 matrix. So let's just come to another 2 by 2 array, since there is no multiplication, equal to M inverse. M what? Inverse. That's matrix inverse. As you can see here, returns the inverse of a matrix for the matrix stored in an array. So you just select it, then you come and what? You select it, you highlight the array, Control Shift what? Enter. Are we together? So you have what? The inverse of this our product. I hope you're following it, which is actually equivalent to what we have here, right? Good. It's actually equivalent to what we have here. Maybe I should expand it so that you can see all the numbers completely. Good. So it's actually equivalent to what we have here. So we are done with the first part of the formula. The first part of the formula says what? A transpose P A inverse, which is this. A transpose P A inverse, which is this. Now let's go to the second part of the formula. The second part of the formula is what? A transpose PL. A transpose PL. So we already have our A transpose P, which is this, right? We already know what our A transpose P means, which is this. So what we are now going to do is that we are going to multiply it with what? L, or we are going to multiply it by L. So now what's our A transpose P? Our A transpose is what? 2 by 5 matrix. And then our L matrix is what? 5 by 1 matrix, right? So by the time the both of them multiply, we are going to have what? Just a 2 by 1 matrix. Are we together? We are going to have a 2 by 1 matrix, which is this. So now let's define our array, which is a 2 by 1. So we say equal to, what's the next thing? A transpose P. What's our A transpose P? This is our A transpose what? P. Sorry. We are going to say M mod. So we say M mod because we are multiplying two matrices. So we have what? A transpose P, comma, L, which is what we have at top here, right? Then Control Shift Enter. You see, these values are actually the same values as we have what here, right? Good. Now the final step, which is our D, is equal to what? This first product we have here, A transpose PA inverse, multiplied by what? A transpose PL, right? Good. So now if you look at it, what's our A transpose PA, which is according to this is a 2 by 2 matrix, and then what's our A transpose PL is what? A 2 by 1 matrix. So by the time you multiply the both of them together, you are supposed to have what? A 2 by 1 matrix, right? So we define a 2 by 1 array. Then we say equal to M mod again, right? Upon typing M mod, what's the next thing we are going to do? Remember, we are starting with this inverse. Where is this inverse? Which is this, right? Comma, A transpose PL, right? Which is this. Then Control Shift Enter, which is this, equivalent to what we have here. Now remember that there is a negative sign attached to the old formula, because the formula is what? Minus in a bracket, a bigger bracket into a smaller bracket, A transpose PA raised to power the inverse, let's say raised to power minus 1, multiplied by A transpose PL. So all of those two products are multiplied by a negative sign. They are multiplied by what? A negative sign. So we just have something like just do something like minus this, enter. So that's how we got this final answer. Then we just drag it down, right? So we have the equivalent of D. I hope this thing is very, very simple. I hope it's very, very simple. So the final thing you are going to do is what? What's the delta is thing? Let's call this for C, let's say the northings and then the eastings, right? Good. So what's the delta northing of C? The delta northing of the provisional, sorry, the northing coordinate rather, the northing coordinate of C given to us, the provisional northing coordinate of C given to us is 12184.52, and then the provisional coordinate of the eastern coordinate of the provisional coordinate is what? 8533.38, right? Good. So we are now going to apply this to what? To each of these coordinates to now get the corrected or the most probable, let's call that, to now get the most probable coordinate. Is that the most probable value of the coordinates of C? Are we together? So the 0.13 represents the eastern, whereas the minus 0.22 represents what? The northern. So this will now be equal to the corrected. Let's call this corrected. Let's call this corrected. Then let's call this provisional, right? Sorry, that's provisional or something, right? Good. So let's do this. Good. So this corrected will now be equal to our 0.2 minus 22 is that of the eastern. This plus this our value here. Then this is also equal to this plus this value here. Therefore, these two values are the adjusted or the most probable coordinates of what? Of our station C. I know it was quite long, and I also know it was quite exhaustive. If you had actually followed us to this point, thumbs up to you. You can actually encourage us by liking this video, subscribing if you've not subscribed, sharing it with your friends and your colleagues. And if you have any issues regarding this or related to this, you can actually contact us with any of our contact details on the channel, and we'll get back to you as soon as we can. So we hope we've provided solution to this particular solving problem. Thanks for coming to class. We are going to see you on our next video. Until then, keep being good at what you're doing, keep making observations that can be adjusted, and we'll see you soon. Bye.